looking to the future. You turned in homework for today, right?
Yay.
You did 5 today, so I guess it must be 6 that's pumps. There we go. Because 5 was the loop method and water hammer. All right, so homework 6, pumps, is due on Wednesday the 26th. We're also scheduled to have our exam that day. A week from today, the exam. More information about that to come, but just to put it on your schedule, that's what we're aiming for. Any questions related to the announcements or scheduling issues? Jeffrey?
So is it going to be mixed concept and mathematical questions?
On the exam?
Yes.
I don't know if there will be any concept questions. I mean, I don't think there will be any short answer type stuff. I think it'll all be calculation.
Okay, I'm just curious.
Yeah. Any other questions? Yes.
Will Excel be on the exam?
Yes.
So we gotta bring our own laptops on the Wednesday. Okay.
That's right. Yeah, you'll need to bring a computer for the exam. Yeah.
Will Excel take up the whole exam?
I think you'll have some questions that you don't use Excel on.
Okay.
So use Excel for one or more question. Boy, I wish we had more time than 50 minutes for the exam. Because that, it's bad for you because it doesn't give you enough variety in the types of questions that you're asked to solve. I can't give you a loop question and a 3 reservoirs question and, I have to choose. And it would be good if you got a little bit of everything. So I'll try and strike a balance. All right. Any other questions before we start talking about cavitation? All right. So here's that diagram that we looked at previously on Monday when we were discussing pumps. And the issue with these pumps is that the suction side of the pipe, the pressure is going below atmospheric pressure. So in absolute terms, our standard pressure is 101,325 pascals. And that's the pressure of the water where the air and the water are in contact with each other. Of course, if we go down through the water, the pressure is increasing. But then when we go up through the water, the pressure is decreasing. And the pressure is especially decreasing as we go in the direction of flow because of the effect of pipe friction. So as we're getting from the downstream, as we're working from upstream towards downstream, as we're getting closer to the pump, we've experienced more and more head losses due to pipe friction, and so the pressure is below atmospheric pressure. And when the pressure gets below the vapor pressure of the fluid, then that's when cavitation can occur. And cavitation is when bubbles that are the liquid itself, it's not, come on in, cavitation. It's bad. It causes damage to impellers. We want to prevent cavitation. So the way that we can calculate whether cavitation is likely to occur is this formula. And what you're calculating is something called the available net positive suction head. And you can think of it as a safety factor of how far away you are from cavitation. And each pump manufacturer will give you the required NPSH. And that's kind of the minimum suction head that's required to prevent that pump from cavitating. And so if we look at this formula, what's in this is you begin with atmospheric pressure. And all the other terms are subtracted from atmospheric pressure. Now this is going to be in units of length. It's the pressure head minus the elevation difference between the water surface and where the pump is located. And so the Z sub S is just talking about the suction side elevation change minus the head losses on the suction side pipe only. And those head losses include both the friction losses and the local losses, and then minus the vapor pressure. Now, the bigger NPSH is, the further away you are from cavitation. But if NPSH is small, then you approach the risk of cavitation. So think about, in this formula, which things would give you a small NPSH. So if you have a big elevation difference, meaning that the pump is lifting the water, a big elevation from the suction side to the pump. So if there's a big elevation difference, that means that there's going to be a larger negative pressure, and I'm speaking in gauge terms there, negative below atmospheric pressure before the water gets to the pump. Or if you have a really long suction side pipe, then you're going to have large head losses. And so a really long suction side pipe increases the risk of cavitation, because what it's doing is it's spending the currency of this atmospheric pressure. So here are the terms of the NPSH formula, and the required NPSH increases with increasing flow rate. And it's a physical characteristic of each pump being a little bit different, and the manufacturer will tell you at a certain flow rate how much net positive suction head is needed. And here's the criteria, that if the requirement is greater than what's available, cavitation occurs. And so that's the analysis that we do in these cavitation problems, is we try and find out if the requirement is above what's available, and if it's equal, there's this technical term called incipient cavitation. It means that's kind of the threshold at which cavitation begins. And so if the question is asking, like, what's the maximum elevation difference that could be tolerated before cavitation occurs, then what you would do is you would set this net positive suction head available to the requirement, and then you'd solve for the unknown delta Z. Yeah?
Wait, what is the A and the R stand for?
A is available, R is required. So a pump manufacturer will tell you the requirements, and the system dictates what's available. Okay, so here's an illustration where we're lifting water from a lower reservoir up to the higher reservoir. Now, we don't have any information about the pipe or the elevations after the pump. For these NPSH calculations, we're only looking at the flow between the reservoir and the pump itself. And so the delta ZS is talking about what's the elevation difference from the water to the physical location of the pump. This head loss term is just talking about the head losses that occurs on the suction side. And even though there are head losses after the pump, they don't do anything about the risk of cavitation. So it's just the suction side losses that go into the formula here. And of course, we can understand the vapor pressure of a fluid by knowing the temperature of that fluid. And so here in the case of water at 40 degrees Celsius, for instance, the vapor pressure of the fluid is 7,300 pascals. Okay, so in this example, the manufacturer tells us that we require 3.5 meters of NPSH. So what I'd like you to do is calculate what is the available NPSH and then compare it to the criteria. And the criteria is if requirement is bigger than available, then cavitation occurs. But if the requirement is less than what's available, then there's no cavitation. All right, so let me pause for a moment while you start to substitute into that formula. Okay, so we substitute in the pressure, the suction side elevation change, the suction side head loss, the vapor pressure of the fluid, and it looks like we have available 3.761 meters of net positive suction head. So you can think of that as that's going to be the pressure of the water just before it goes into the pump. the pressure head of the water just before it goes into the pump. And since it's greater than the requirement, which in the problem statement it said that the requirement amount was 3.5 meters, right? So since 3.7 is greater than 3.5, the available is more than what's required. In this case, there won't be cavitation. But we're pretty close. We're flirting with disaster if you think about it, because all it would take for us to have cavitation is what happens if that source tank starts to get drained. And so the water level right now is such that there's 4.3 meters between the water level and the pump. But how much further can the water level go down before cavitation does begin? How much can the water level go down before we have a risk of cavitation?
0.76 meters.
No, even less than that, because 3.5 is, isn't it? 3.5 is the requirement. So if the water level goes down to like 4.5 meters between the water surface and the pump, then we're real close to cavitation. If it goes down 0.3 of a meter, so if it goes down 30 centimeters, then cavitation is going to occur in the pump. So, you know, a big delta Z is one thing that can get you closer. Or what if somebody said, well, we just need to move the pump a little bit further away. You know, we're not going to raise the pump because we know that's risky, but we can't have it that close to the water. It might get splashed on or something. So we need to move it further away. And so if you make it a longer segment of pipe, then you might end up having more head loss. Now here, just for sake of simplicity, we didn't actually calculate the head loss, but in a real situation like this, you'd either use the Hazen-Williams equation or Darcy-Weisbach equation to calculate what is H sub L. And so think about the factors that can promote a big head loss. If you have a small diameter pipe, you have more head loss than a large diameter pipe. And so if you're perceptive and you look, oftentimes what you'll notice is that in a suction side, the hose is a larger diameter than in the discharge side of a pump. That's something that I've seen in lots of lab scenarios where they're using pumps to draw water up out of a storage tank. They use a large diameter pipe on the suction side because if you have a lower velocity, then there's going to be less head loss. And so therefore it's less risk of cavitation in that sense. There's one more thing that could promote cavitation. We've already talked about if the delta Z was increased, or if the pipe length was longer, or if you had a smaller diameter or a more rough pipe. Any of those things that promote additional friction would promote cavitation by making H sub L term larger. How does water temperature affect the risk of cavitation? What's more likely to cavitate, warm water or cool water? Warm. How come? Why?
Lower vapor pressure.
Close. It's because warm water has higher vapor pressure. So remember, under ordinary pressure, the vapor pressure of water at 100 degrees Celsius is 101,325 pascals. And so the vapor pressure goes up with temperature. And so if the water is 90 degrees, it's already so close to boiling that it's not going to take much additional suction pressure before it gets there. And so cold water is further away from boiling. And cavitation and boiling, that's the same thing. It's the process by which liquid water is going into gaseous water, so water vapor. And so here, in this example, we had water at 40 degrees Celsius, and the vapor pressure is 7,300 pascals. If it was water at 99 degrees Celsius, then the vapor pressure would be like 100,000 pascals. And then it's going to cavitate in that sense. And so that's another factor that could promote cavitation, is the warmer the water, the bigger the risk. And then something that you have no control over, but to be aware of, is that atmospheric pressure is another factor. And there are places where the atmospheric pressure is going to be less than standard pressure. The standard sea level pressure of 101 kilopascals isn't the same as the atmospheric pressure at the top of Mount Everest. I think the atmospheric pressure there is more like 70 kilopascals. And so if they're pumping water at the top of Mount Everest, they got to be careful of cavitation because they don't have this first term isn't going to be as big as it ordinarily would be. So it's not just Mount Everest. There's other high elevation places that are inhabited. So that's cavitation. Any questions before we move on? All right. Let's do another example with pump operations. This is the same stuff that we did in class on Monday. Remember that for finding the operating point, what we do is we set the system curve equal to the pump curve. The pump curve describes the performance of the pump as a function of flow rate. And this H sub P is how much head the pump is adding. The system curve we get by substituting data into the energy equation. So here on the left side of the screen is some information about this system. We're drawing water from a reservoir, discharging it as a jet at some elevated location. And so 1 in the energy equation is the source, being the tank. Location 2 is this jet of water as it discharges out of the pipe. We know the total length of the pipe is 135 meters. Just to simplify things, we're going to go with a fixed F value so that you don't have to go through the trouble of starting with the fully turbulent assumption and then checking it later on. Let's just use a fixed F value in calculating the pipe friction. But we want to know what's the operating point. You know, when you match this pump with this system, what flow rate is going to be passing through here. And so then therefore here in A it's asking how long will it take to pump 1 metric ton of water. Have you heard that term before, a metric ton of water? What do you suppose a metric ton is? A normal ton, a standard British gravitational units ton is 2,000 pounds. A metric ton is 1,000 kilograms. So a metric ton is actually more than traditional ton because there's 2.2 pounds in a kilogram. So that'd be 2,200 pounds. So how long will it take to pump 1 metric ton of water? So that's a cubic meter. So there's 1,000 kilograms in 1,000 liters and 1,000 liters in a cubic meter. So anyways, all right, so find Q. Let me give you a sneak peek of where this is headed. Wait. Yeah, maybe I think I... All right. So location 1 is the source tank. Location 2 is just a stream of water. So there's still velocity head at 2. And when we cancel things out in the energy equation, we're going to have to keep that in mind. All right, so we know the F value, the length, the diameter. We can calculate the area from the diameter. The delta Z is known. So if we rearrange in terms of H sub P, because we're going to try and set that equal to the system curve, the system curve equal to the pump curve, then the elevation that it has to lift the water is 12, and then there's all these other things that also contribute to how much pump head is required. And so there's going to be the velocity head term that exists because V2 is not 0. V1 is 0 because it's coming from a reservoir, but V2 is some unknown velocity. And we can also express that velocity head as Q squared divided by 2GA squared. So there's the velocity head, the local losses, and the friction losses. And those three terms each contribute to the additional energy that the pump has to add. So we have to add at least 12 meters of head just because of the elevation difference. But then we also have to add a little more energy because the water's still going to be moving at location 2, and we have to add enough energy to overcome the local losses and enough energy to overcome the friction losses. And so we can factor those three things together, and you can see that what I said here is it's 12 meters of head because of the delta Z, and then q squared divided by 2ga squared multiplied by the velocity head factored out, the local losses since our k value is equal to 1, and then the friction losses. Everything factored, the 2ga squared in the denominator, the q squared factored out. What's left is the friction factor, the length, and the diameter. So this is kind of the structure of the system curve. And we can substitute in the known A and the known friction factor and length and diameter. And with that, here's our system curve. You can think of this 282.1 as similar to the R values that you calculated in the loop method. It's kind of like a resistance factor. And the bigger that resistance factor, then the more pump head is going to be needed for a certain flow rate. So what we do is we set this system curve equal to the pump curve, the other formula that expresses H sub P in terms of Q, and then solve for Q. Okay, so we have a system curve that's just us substituting the known information into the energy equation, and the way that you find the operating point is set the pump curve equal to the system curve. So we knew that HP for the pump curve, and we set that to the HP for the system curve, combine like factors, we get this equation 6 is equal to 287.7 q squared. So the flow rate should be 1.44 cubic meters per second. And now that I know the operating point in terms of the flow rate, Q, I can calculate the pump head that's required to achieve that flow rate. So you can see here that I calculated what HP corresponds to our flow rate. And if we're trying to figure out at this flow rate how long it will take to pump a volume of 1 cubic meter, then the time required to pump that volume is volume divided by Q. So 6.9 seconds it's going to take for the pump to lift a ton. And then the second part of the question is asking about the electrical requirements. And so factoring in the efficiency, how much power is required? And so we know the pump head, the H sub P, from having calculated the flow rate into one of the two equations that describes H sub P in terms of Q. So we know the flow rate, the unit weight of the fluid, the pump head that's being added, and that's 17.85. And then divided by the overall efficiency factor. And since we have a separate efficiency factor for the motor and for the pump, we combine them by multiplying the two together to find the overall efficiency factor. So this pump is going to be consuming a lot of electricity, 48.5 kilowatts. And just to put that in perspective, a typical residential home, even when the air conditioner is running, is maybe only going to be drawing 5 to 10 kilowatts. So this single pump is taking between 5 and 10 times as much electricity as a house on a hot summer day. So that's what it takes to lift 1,000 kilograms of water that distance in just 7 seconds. 12 meters is pretty high. I couldn't lift 1,000 kilograms 12 meters in 7 seconds. Probably take me 8 or 9 at least. But question?
How come for the HP, for the equation you put 12 plus watt?
Okay. That was the system curve. So, this system curve that we came up with, the 12 is the elevation difference, and then plus the other stuff is all the other energy that's required for both the velocity head, the friction losses and the local losses. So I could have substituted this Q, the Q rate, flow rate here, I could have also substituted it into this equation to find out what pump head is required.